So, lecture 3.3, approximate analytical transient response characteristics. So, let's remember what we've done in this chapter so far. In lecture 3.1, we introduced some transient response performance criteria, right? We defined 4 different quantities. We defined the percent overshoot, which all of these quantities are defined in terms of the step response of a system with 0 initial conditions. So we defined the percent overshoot. We defined the rise time, the settling time, and the peak time. Those were the 4 different quantities that we defined. And we defined them just in terms of lengths of time to get to a certain feature in the response, or intervals of time for a feature to emerge, and then also relative height in the percent overshoot case, or a relative quantity of the response. So relative to the steady state value. So those were the 4 that we defined. And in lecture 3.2, we took those definitions and we derived, in some cases, and in some cases I just gave you the solution for, what those 4 response characteristics, how they relate to first and second order system parameters, so time constant, natural frequency, damping ratio, for systems without zeros in them. Okay, so that was the lecture 3.2, and so we can get these exact analytic values in these cases. Now, unfortunately, I know it's disappointing to discover that not every system is a first or second order system with no zeros. It's just the truth. I'm here to tell you. So we can have higher order systems. We can have systems that are lower order, but they have a 0 or 2 associated with them. So when those arise, it would be nice if we still could relate our nice our first and second order parameters to these performance characteristics, even though we don't have this perfect solution that we had in lecture 3.2. Maybe we can get an approximate solution. So that's what we're going to talk about in this lecture, and that is that certain higher order systems can be approximated as second order systems and can be characterized by the parameters in the preceding section. So we can still use those parameters. We can still relate the percent overshoot to the damping ratio, for instance, even though it's a third order system, say, or a 10th order system. This includes systems with zeros. In the preceding section, we assumed the second order system had no zeros. So we also will consider that. So these conditions are as follows. So these are the conditions for the second order approximation, is the one that we'll most frequently use, for when that assumption applies, or that approximation is accurate. So let's just remind ourselves what the Polezero plot looks like. So if you've got, say, a second order pair of poles, we know exactly what the relationship is between the natural frequency, damping ratio, and even the geometric locations. If you go back to lecture 3.2, we had this as our geometric representation of a second order system with a complex conjugate pole pair, or overdamped as well. And we have this sort of like radial natural frequency here, and we have the damping ratio related to the angle. And these parameters, even for higher order systems that have more poles and more zeros, sometimes we can use, and we would like to use them. They're going to be really useful for us. So we're going to see, when is that still valid? And that's what this lecture is all about, 3.3. When is that still valid? So the first one is higher order poles are significantly leftward. That's like the summary. Unpacked a little bit. Higher order poles have significantly more negative real parts than the dominant second order poles. So a more negative real part would put it over here, right? Or you could have a pair of them over here. But as long as these guys are quite a bit further to the left, or more negative than the dominant pair, okay? Why is that the case? Why does the fact that these ones are out here mean that we can kind of assume that they're not going to have a big contribution to the transient response?
Because they decay so fast.
Exactly.
They don't make a significant contribution.
Yeah, so remember these poles are going to govern in the homogeneous solution the exponent here. These exponential decays if it's stable. So these exponential decays are going to decay with a rate associated with the real part of the poles. And if that's a large negative number, large magnitude negative number, then we have like e to the negative 100t. So even in the first time step, if you got one at e to the negative 5t, the first time step, e to the negative 100t is going to be decayed way more than the one that's closer to the axis, the one that has a smaller magnitude. So we are, so we can say these guys are, we can ignore them, and we can say that the exact solution is approximately true for a system that has this situation. A guideline is that they should be at least 5 times as negative. So what we would do is we would say, okay, a typical guideline is, and this is an arbitrary number, 5 times, but this distance versus, this distance is like 5x. That's a sign that you're going to have a pretty good approximation. Okay. Great. So the next condition is that higher order closed loop poles and zeros nearly cancel. So closed loop zeros near the closed loop second order pole pair are nearly canceled by the close proximity of higher order closed loop poles. So maybe you've got a troublemaker pole that's right in here. It's troublemaker in the sense that it kind of messes with your second order approximation, right? Because there's a pole that's kind of close to the other poles. These two that you are thinking are going to dominate the response might not actually dominate the response. So you can kind of get rid of this guy by putting a 0 close to it, or on top of it. Now, before we get too enamored with the concept of pole zero cancellation, remember, say this was at -3. This would correspond to an s plus 3 0 and an s plus 3 pole, and they would effectively cancel. But before we get enamored with pole zero cancellation, there is a concern about stability still. If you have a right half plane pole, and that means it's unstable, right? And you put a 0 on it, it does cancel, and in terms of forced response, technically, it will be stable. However, if there's any disturbance in your system from equilibrium in that modal direction, which doesn't make sense from what we've talked about so far, but you might have a concept of what that might be, the system will still go off to infinity. So it's still unstable even if you have pole zero cancellation of an unstable pole. Yes?
So is that graph, is it, like, what are the units of it? Is it a linear graph, or is it like in dBs, like this stuff? Or?
This is the complex plane, the pole zero plot. So complex plane, the pole zero plot. So we've done pole zero plots before, And I mean, that was what we did in this lecture, right? We put the poles here, the imaginary axis, the real axis. This comes from the fact that in our transfer function, S is a complex number, right? It has a real part plus an imaginary part. And so this is the sort of map, the real and the imaginary map we're using on in this plot, in this figure.
Yeah,
So
but like the actual units of it's a linear one, right? So it's like -1 to infinity or negative infinity.
yeah, I mean, this is just the entire plane. So any real number, so you have the real axis, and you have the imaginary axis. And this can be any real number. So you have a coordinate here, which is a pair of numbers, a real number, which we often call sigma, and an imaginary number we often call omega, or an imaginary component we often call omega. And these can take on any real number value, so positive or negative, each of them. So this point can move around in the entire plane. In terms of the units,
Wouldn't sigma be like 1/tau, basically?
Well, the transfer function is defined as the output over the input. And so the units effectively of the numerator are going to be in the output units, and the units of the denominator of the transfer function are going to be input units. So the way that this typically works in practice is you choose a consistent set of units. So SI or English is fine, but use the base units of each of them. So if you always use kilograms, and you always use meters, and you always use seconds, and you always use amps, and you always use volts, etc., then whenever you find a quantity and you know what the unit of that quantity should be, if it's current, say, you know you're going to get it in amps. If you use millivolts or something, then you got to figure out what your units are going to be. But yeah, I think that the units question is an interesting one. I think that effectively using the output units for the numerator and the input units for the denominator is valid. It does depend on the transfer function, like what the units are that went into the transfer function definition. So yeah, like if you use your mass in grams, then you gotta like keep track of what that is going to be. So your output could be in, say it's like a mass flow rate. It could be like kilograms per second, I guess. But if you used grams when you put your mass parameter in there, then it would be in grams per second. So, yeah. Okay. Good. So, then higher order closed loop poles and zeros, the cancel, we talked about this. There can be this cancellation, but we have to be a little cautious, especially if there's any unstable pole associated with that. Uncancelled closed loop zeros are distant from dominant poles. So that would be the case if we've got some zeros out here. Once again, these aren't going to affect these dominant poles very much. So yeah, so that's the gist of it. So what we want is to understand that this approximation, using the second order approximation, for instance, is valid as long as we are being cautious about how good of an approximation this really is. And I would say what we'll often do is we'll assume in any case, probably, that it'll be about second order when we do our design process, even when that's not true. And the reason we do that is that even if it's not valid, it gives us a starting point for our design, even if the approximation doesn't hold very well. If it holds perfectly, we don't need to do any follow-up after that. Like, we can just be like, oh, okay, well, it's exact, so we don't need to do like a simulation to check to see if it'll be the case, because it will certainly be the case. I mean, you can. Maybe you were wrong about something, and so it's good to check things multiple ways. So yeah, we're going to use this approximation in most cases anyway, even if it's not valid, but know that we're also going to check in most cases too, just to make sure that it works. So you might say something like, okay, I want the settling time to be less than X, say less than 3 seconds. Well, maybe the settling time should be less than 3 seconds according to the second order approximation, okay? So you're like, oh, okay, according to the second order approximation, this should be the case based on this parameter that I've chosen. Okay, excellent. If that is perfectly true, if you have the second order approximation that's like actually a second order system with no zeros, then you're going to get that settling time you expect, exactly. But maybe it's just an approximation, and you'll get, instead of 3 seconds or less, you're going to get 3.5 seconds or 5 seconds for settling time. Well, you didn't quite meet your criterion there, so you got to go back and tweak your design to try to make it meet the criterion. So, but it gives you at least a place to start. Otherwise, you're just picking a number out of a hat, right? So it gives you a place to start, and that's usually how we do it. We try to like whittle down our design space to something that's a little smaller to choose parameters from, using an approximation technique. All right.